Hey guys, welcome back to chapter 10 where we are talking about intermolecular forces. Today we're going to dive a little bit deeper into London dispersion and talk about different things that are affected or affect London dispersion. So just as a quick review, London dispersion are fleeting temporary attractions. So these are non-polar molecules, well all molecules, but non-polar molecules that have these kind of instantaneous momentary dipole moments. So charge is separated, one side's partially positive, one side's partially negative, but as soon as that dipole happens, it disappears. So it's kind of a fleeting temporary. Okay. There are factors that determine the strength of London dispersion. So we need to think about how easily can these electrons be polarized? How susceptible are they to their neighbors influencing them or them influencing their neighbors? How susceptible are these electrons to being kind of moved around, shifted around? So the first thing that's going to determine the strength of dispersion forces, or the first thing that's going to determine how susceptible these electrons are to being changed, is the size. So the larger the atom or molecule, the more susceptible those electrons are to being moved or changed or polarized. Okay. So if we think about the size of an atom, so let's just start right there with an atom. What do we know about atoms? So here we're looking at our noble gases, right? So we start with helium at the top of 18 or 8A, and we move our way down to xenon at the bottom. So what we see is from top to bottom, those noble gases get bigger, okay? When we're talking about electrons that are susceptible to change, or when we're talking about electrons being momentarily polarized, we're talking about the valence electrons. So the electrons that we talked about for bonding are the same ones that we're talking about here. Remember, those valence electrons are found in the outermost shell, right? They're the furthest away from the nucleus. So if we think about the valence electrons for helium, we've got this nucleus inside of helium, and in that first energy level is where we find those valence electrons. So they are very, very close to that nucleus. As we move down the periodic table to, let's say, xenon, we've got our nucleus in the middle of xenon. Now our valence electrons are in a much higher energy level. So they're in 5th energy level. Okay? So now we've stacked different energy levels. Our valence electrons are all the way outside here. And those valence electrons are a lot further away from the nucleus, which means those valence electrons are a lot more susceptible to outside influence. If we think of the nucleus as kind of their home base, they are very, very far away from home. And they're more susceptible to change being that far away. Okay. So helium is small, not very susceptible to outside influence. Xenon is big or large, and those electrons are more susceptible to change. So the London dispersion for helium would be a weaker attraction or a lower London dispersion force. And for xenon, it would be a much stronger attraction or a higher, stronger London dispersion force. Okay. We'll talk more about this in later slides, but one of the characteristics that we can observe and link back to strength of intermolecular forces is the boiling point. So this would be a characteristic that we could observe. The boiling point for helium is at 4.2, and then the boiling point for xenon is much, much higher at 165. So this to me is another indication that The helium has a weaker London dispersion force, and xenon has a much stronger London dispersion force. Very closely related to size is going to be the shape. So the shape is going to talk about the opportunity for these interactions to happen. So if size was the susceptibility to change, the shape is going to be the opportunity for change. So here we see 3 different organic molecules. Now, I know you guys haven't had a lot of time or experience looking at organic molecules, so if this looks unfamiliar or weird at first, it should. But we're going to get more practice this chapter looking at these bigger molecules, so just kind of trust the process and continue to work through them. So all 3 of these molecules are pentane molecules. So what that means is all 3 of these molecules have 5 carbon atoms. What's different about the carbon atoms is the way that they are connected together. So I'm going to start over here on the right-hand side. This in pentane, the carbon atoms are connected in a chain. So if I were to just look at the carbon atoms, what I would see, let me get my pen here. Okay, so what I would see here is if I were to look at these carbons, I would see something like this. So carbon, 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 carbon. Right? So they'd be connected in like a straight chain. Okay? If I look over here at the neopentane, the difference here is it's still, well, there's still 5 carbons, but the difference is how the carbons are all connected. So if I look at how the carbons are connected for the neopentane, it would look something like this. So what I see is a much more compact structure. What I see are the carbons are in this kind of like, it looks like a square, but remember that's a tetrahedral shape. So it's a much more compact structure. So if I look at these 2 molecules in 3 dimensions with, of course, the hydrogens around them, what I see for the N-pentane is this long kind of snaking looking molecule. And what I see for the neopentane is more like a sphere or a ball, right? So it's all crumpled up like if you were to crumple up paper into a ball, that's what it looks like. So when we talk about this shape and how it determines the strength of London dispersion, for the N-pentane, we have all of this surface area where these dipole moments, these London dispersion moments can take place, right? So any of these positions on the molecule, we can have one of those fleeting, momentary separations of charge. Over here on the neopentane, it's a much smaller surface area. So these 2 molecules do not have as much surface that come into contact with one another. Therefore, the opportunity for that dispersion to take place is much, much smaller than it would be for N-pentane. So the larger the surface area, the more opportunity for interactions, the stronger that dispersion strength is going to be. The smaller the surface area, the less opportunity for interactions, the lower that is going to be. So how do we determine, like I look at 2 molecules and I'm like, is that a bigger molecule with more surface area? Is it a smaller molecule with less surface area? What's the easiest way to kind of determine these? So for size, remember we can look at molar mass. So we can add up all of the atoms. We can look at the molar mass, and the bigger the molar mass, the bigger the molecule is going to be, right? For shape, that holds true as well, as long as the molar masses aren't the same. So in this particular example, the molar masses would have been the same, so that wouldn't have worked. then we've got to look at these three-dimensional pictures. For organic-y type molecules like these, I will provide the picture for you. I don't expect you to know how to draw those yet. That's not in your wheelhouse. But for other molecules that are covalently bound, there may be some times that I do ask you to draw them because that is in your wheelhouse. So shape, you would have to draw the structure. For the size, you can look at the molar mass. So just to kind of in conclusion, the heavier the molecule and atom, the stronger the dispersion force will be. Lighter molecules, lighter atoms, it'll be a weaker force. Larger atoms have greater polarizability, and that's just due to the valence electrons being further away. So the atoms being larger, those electrons are more susceptible to change. And then when we talk about the larger the molecule, we typically are talking about surface area, more opportunity for interaction. Okay. So that is just some factors that affect the strength of London dispersion. From here, we're going to move away from London dispersion and start talking about the other intermolecular forces. I hope you guys found this helpful.